Hello, it's a pleasure to present our ICLR 2025 paper, SPA, 3D Spatial Awareness Enables Effective Embodied Representation. In recent years, the research community has shown increasing interest in embodied AI, where agents must perceive, reason, and interact within complex 3D environments. Developing a general policy for such agents requires robust and generalizable representations. Current visual representation learning methods for embodied AI primarily draw inspiration from 2D vision paradigms, relying heavily on contrastive learning or masked autoencoder approaches. However, these methods often struggle to effectively capture the spatial relationships and 3D structures inherent in the physical world. In this paper, we propose a key spatial hypothesis: 3D spatial awareness is crucial for embodied representation learning. This hypothesis is supported by several observations. First, prior work has demonstrated that incorporating explicit 3D data structures, e.g., point clouds, significantly enhances policy performance. Second, since embodied AI policies typically process observations and generate 3D positions and rotations as actions, the problem can naturally be framed as a 3D regression task. However, existing observation modalities present trade-offs. Point clouds provide explicit 3D structure but are difficult to scale in terms of both data and model size. Images are easier to collect and process but lack explicit 3D structure, limiting their robustness for policy learning. This raises a natural question: can we combine the advantages of both? We propose multi-view images as a solution, as they retain the scalability of images while implicitly encoding 3D structure information. To address this challenge, we introduce SPA, a general 3D spatial-aware representation learning framework for embodied AI. SPA leverages neural rendering as the pre-training pretext task on multi-view images. Unlike explicit 3D representations like point clouds or meshes, multi-view images are easier to process and more readily available, making them ideal for large-scale training, such as from internet videos. Specifically, given a vanilla 2D image backbone, e.g. a vision transformer, we first extract multi-view feature maps from the input images. Using known camera poses, we then construct a feature volume from these feature maps and sample rays to apply differentiable neural rendering. This process generates multi-view RGBD images and semantic maps for supervision without labels, enabling the pre-training of a 2D image backbone to enhance 3D spatial awareness. Another problem is that, unlike the CV or NLP communities, where large-scale benchmarks are common, embodied representations have not been thoroughly assessed. The largest previous evaluation, VC1, includes only 17 tasks. This may lead to randomness and bias. Therefore, we have created the largest embodied evaluation to date, encompassing 268 tasks across 8 simulators, over 15 times larger than VC1's evaluation. Additionally, unlike previous approaches that used a small MLP policy under single task settings, our evaluation spans multiple policy types, e.g. MLP, diffusion, transformer, and includes both single task and language-conditioned multitask settings. This unprecedented scale and diversity ensure robust and convincing conclusions. Through extensive comparisons with state-of-the-art visual representation methods, we observe that SPA demonstrates superior performance on our large-scale evaluation on average. We also find that focusing on a single benchmark can lead to highly biased conclusions. For instance, ImageNet pre-trained methods, e.g. MoCo V3 and May, perform exceptionally well on the Franca Kitchen benchmark, suggesting a minimal domain gap between ImageNet and Franca Kitchen observations. These observations underscore the importance of our large-scale embodied evaluation. We also visualize performance using radar charts and pie charts, demonstrating SPA's superiority in both mean success rate and mean rank. Furthermore, to prove our spatial hypothesis and demonstrate that SPA has acquired 3D awareness, we provide both quantitative and qualitative evidence. For qualitative analysis, we visualize the zero-shot feature maps on multi-view images of different encoder outputs. The images are taken from the Unseen ArcIT Scenes dataset. The feature map visualization provides clear evidence that SPA has learned multi-view consistent knowledge, demonstrating its 3D awareness. Additionally, the features produced by SPA are cleaner and more coherent. Though VC1 also generates smooth features, they are not consistent across viewpoints. The feature maps from the multimodal approach are highly noisy and lack details. For quantitative analysis, we evaluate the zero-shot 3D awareness of various methods using a camera pose estimation task. Specifically, given a pair of images from different viewpoints, we use a frozen encoder to extract features and concatenate them. A small MLP then regresses the relative camera pose and we report rotation and translation errors. We observe that SPA outperforms all other methods in zero-shot camera pose estimation. It achieved an 18.3% improvement in translation and a 15.3% reduction in rotation error compared to the second-best model. Additionally, we identify a clear positive correlation between camera pose estimation and embodied evaluation performance. This finding supports our spatial hypothesis and may offer valuable insights for future research on embodied representation. Finally, we conduct several real-world experiments to further investigate the generalization ability of different representations. The robot performed 2 single-arm tasks, picking a cube and stacking a yellow cube on a pink cube, as well as 1 dual-arm task, folding a cloth in half. As the results shown, SPA consistently performs better on real-world tasks, suggesting that SPA's pre-trained representations can robustly adapt to real-world environments without fine-tuning. Thanks for watching, and welcome to visit our website and GitHub repository for more information.